For millions of years, humanity on this planet has lacked knowledge about how brains work in computational terms. And now we face two major challenges. On one hand, humans fight wars and oppress one another. On the other hand, modern-day general-purpose computers still lack human-like intelligence. After years of cross-disciplinary study and research, we have begun to understand how the brain works in computational terms. Knowledge like this can help resolve human conflicts and enable us to create smarter machines. This series is about brain mind and is here to entertain and inspire you.
Today we talk about, continue from last time, we'd like to talk about the DN2 self-organization. So last time we already had an architecture. Somehow that, let's look at this, still have a something like Z. Alright, Z is our muscles, and we have X, pixel values, and normally will be RGB, but we just use intensity for num, and Y we have a bunch of neurons. And last time we talked about patterning, so we have a different connection of the Y neurons. And let's look at, say, you have neurons that firing, and with connection. Originally, we assumed that connection is complete. Last time, we did not say that with a complete, not supposed to start with a complete, all right? And that's Z only. And today I want to talk about the complete connection, which is type 1-1. Patterning type 1-1-1, where you have a connection from X. Suppose complete. Complete means that you really have in this case 6 pixels, so you have 6 connections. Then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You have 11 neurons firing. Then this one, self-organization, basically suppose this is the first neuron, the type 1-1-1, mean that at the beginning you do not have any Y neurons, right? So it does not have a connection to itself. And this is the first neuron, and it does not have a connection from a Y neuron, so it does not have anything. And it has a vector. This is a vector called Z. All right, Z is in the set of all Z neurons. All right, all the Z neurons is probably in the space. In this case, is suppose it's a U value of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. So this is the Z. This is all the space vectors, 11 dimensions, and a vector Z is element in that one. So that's what. Then I have a top-down weight, which is extremely important for the DN. All right, very different from all traditional neural networks that has a weight vector here. We called V top-down. All right, that's also a vector in the in the dimension of real value 11 because matched, all right? And traditionally you have x window, then it has this vector. This vector has a weight v bottom up is also a vector in the 11th dimension, all right? And traditionally, yes?
It should be of 6th dimension because it matches.
Yeah, you're right. Thank you. So 6th dimension because 6 pixels. And traditionally, we have a cascade. Cascade means that I have a matchup weight. So give example that VB vector, right, in a plot that with the input x, x, and we typically would like to normalize it, all right, so that be a unit vector, and x will be unit vector. I will do more detail later on, all right. Give example later on, we would like to have a x to have a zero mean. So all these vectors subtract their 6 value mean, then it becomes zero mean vector. And same thing for VB. We like to subtract the weight vectors so that they have a zero mean vector. That will compute this inner product becomes correlation coefficient. All right, correlation coefficient. Say correlation coefficient is B part. All right. Then we like to do the top level part. Top level part is unique, all right? And I have not seen any tangible theory about the top down part. Because top down part is really people have the problem with. And we have top down part is top down part equal VT in the plot with Z and VT and Z. So we have a bottom up part value and top down value and add these together, all right? So that one is a pre-action value. Pre-action value say y equals to RB plus RT. So we have this is called bottom up match value, top down match value. Ideally, if a perfect will be 1, ideally perfect will be 1, so this value will be 2, all right? And ideally will be 2. And to start with, we do not have any neuron. Then we have initial state, Z. It's like the initial state of the final state machine. And the B is the initial state of the input vector. This is a vector, but in the symbolic word, this is like a symbol, right? This is a symbol input, this is the context. Then this one give you the goodness match between the bottom up part and top down part, all right? And that value, without any y value, the first one basically takes this input as its weight. So take the x as the weight of VP, and with the z as a weight of VT, then VB, Vx are the same, VT and Vx are the same, and that turns out to be 1 plus 1. This is a perfect match. So y become perfect match, first neuron and perfect matched, all right? And that y will fire at 1. Prime means that really finding value because it does not have anybody to compete with. Right now is 1. So you can see that when we have this z and x, we already have a vector of a state and an input, and we find the match. This y neuron, this neuron in y, really perfect match z with the top down weight, perfect match x as top bottom up weight. And this is like an entry in the transition table I will draw next, all right? So that's the first one we have, all right? And I'd like to get another piece of paper. Thank you. All right. That's second page, 320, 17. So suppose, thank you. Suppose that I have a Turing machine. I just Turing machine first. Originally, we start with a final state machine. Now we do Turing machine. Turing machine transition table. Ideally, it's not like that. I just use the state vector Q, all right, with input, say sigma. We'll map to a Q prime, and that's FA, final state machine formulation. When we move to Turing machine, we expand the definition of Q to include actions. Originally just state, and we sometimes we draw that way. Q with sigma, we get Q prime. That's FA formulation. We do Turing machine, then Q including actions. Q given up to Q has a state, and originally you have a second example, you have a Q1, then head motion. All right, head motion could be have left, right motion, and stationary, don't move. And that's head motion. But I also have another action, which is typically for gamma. All right, say gamma is the letter you write. The letter write to tape. So you can see that I just do intuitively. For those who are interested, just look it up, the notation, all right? So give example that currently we have a Q original for FA only has state Q1. Now we have gamma. Gamma is the symbol to write to the tape. So for robot, it's the action you apply to the real world, like navigation, move forward, move backward. If I change, that's action, and also could be your hand. Your hand pick up object. The pick up object will change the input of the image. Then this is like a gamma. And a head motion. Then in the Turing machine you have a read write head. And right here, the Turing machines that have a tape, right? TAPE. Then you have read write head, right? Read write head. Then Turing machine has control, right? The control is a lookup table, but F8 does not have, cannot move, all right? F8 does not have a tape. F8 can have an input sequence. Now you can write to the tape, then you can move up and down, all right? All stationary. So this is a Turing machine. And if you expand that definition Q, all right, to include the action and the head motion, then you still can write that way. Just state is expanded. The major difference is that for this state, for Turing machine, it does not look at the gamma and the head motion, all right? Only just state. And this one has action. But it doesn't matter. You can still write F8 as a lookup table, all right? Lookup table like this, except that, for example, that you have input sigma 1, sigma 2, sigma 3. I have a Q state 1, Q2, Q3, and I have a lookup table that many people understand. This is really familiar, all right? Then this means Q1 with sigma 1 equal to Q2, for example, and then Q1 with sigma 2, Q3, Q1 with sigma 3, Q1. So then the next with Q2, you have input Q1 equal to Q3, like that. But now this Q has head motion. Then all we need is just if the FA of the Turing machine, it does not really look into the head motion inside. This is expanded. This is not. But all you need is just disregard this component. So basically, different Qs that have the same sigma, or same Q, but different sigma and H, is not disregarded. So you have identical columns, rows, identical rows for states that are identical in state, but you have head motion and tape right symbols. Then that's expansion using lookup table from FA to Turing machine. This is a major theoretical work we published recently. That basically that Turing machine, in fact, has a controller of FA. So this control turns out to be a Turing to be a finite state automata or finite automata FA. All right, that's a Turing machine. All right, Turing machine. That make our discussion a lot simpler. Now we, instead of using the symbol, we start to do the vectors. So look back, what do we did? This is look back. So now Z is actually for our, this Z is for our Q space. X is for our sigma. All right. Then the Q, little q, for example, Z actually Z becomes Q1, Q2, Q3. Then the X, originally you have a sigma becomes, so this one becomes Z1, Z2, Z3, this become X1, X2, X3, and those instead of symbol now becomes Z2, for example. All right, so this becomes Z2. So you can see that everything becomes vector now. The Y vector, because we want those symbols to go away. We only want vectors because vector can emerge from interactions. So this is our towards automatic programming. We have vectors, and these are the muscles vectors, and the X's are images. They're all emergent through interactions. We do not need a symbol to be in the middle, because once you have a symbol in the middle, then you need somebody to handcraft the symbols. All right. Now, then go back. How this network DN2? I want to explain only a particular type actually goes to by DN1. DN1 has only one type neuron that has a Z and X, but without Y to Y connection. All right, that's DN1. All right, DN1 is only, there's no single Y neuron. Then I explain how it can happen. All right, so this neuron actually match what? We actually use its bottom up to match X1. With top down to match Z2, it perfect matched. If next time you have an input very similar to X1 and Z1, and this neuron will match very well. This match very well, and then if it's perfect, if it's symbol, then it's perfect, right? Because vector corresponding to symbol perfectly, then we'll fire at 1. Pre-action value is 2 and fire at 1. And this one basically that I found that the match.
I think that's type 1 is longer.
Yeah, you're right. Xiang was right. So because does not have Y connection, so it's X, Y, Z, so type 101. Yeah, Xiang is right. So that 101 is the only type available in DN1. All right, I start with DN1 so you can see how it's powerful. So this Y neuron, if fired, means that other neurons do not match as well because other neurons do not have a perfect match, right? Because different X and different Z, then other neurons do not match. So we use top 1 neuron globally for finding the best matching neuron. This match neuron perfect, it becomes pre-action value 2. Then we fire at 1. Other neurons do not fire. If the top K equal to 1, then this is basically perfectly matched. Most particular entry. So for different entry, we have a different Y neuron. Suppose match is perfect. When it's fired, I want to go to say this is the case. You want to go to say Z3, and once this guy fire at 1 as Z3, we apply this one to become Z3 next time. All right, let's see how that happens. Then suppose that we want, this is a particular Y neuron, this is particular Y0, Y neuron, right? So a particular pair of the X and Z represents sigma and Q respectively. We will have a situation like that. Maybe go to the previous first page. The page has a diagram, and this neuron is firing at 1. Other neurons are firing at 0. Other neurons are firing at 0. Suppose you generate many neurons, each neuron corresponding to different inputs. Then we only allow the top 1 neuron firing at 1, other neurons firing at 0. So top 1, then this neuron is firing. And we want to transit for the next time to the correct Z. And what we do is this, all right? And suppose this Y neuron is 1, other neuron is 0. And maybe many. And we still have X, we still have X. We have a Z next time, with Z prime next time. And it was such that I suppose this is 1, this is particular Z we want, all right? And if this is the 1, and we use Hebrew learning so that this is linked, this is linked, this is linked. All other 0 don't link. Why? Because with the Hebrew learning was like it's the input, all right? It's input for Z neuron is Y, all right? Y value has 1, 0, 0, 0, 0. So suppose we have 5 Y neuron, all right? Then if this neuron fire, supervised to fire, then basically it will have the old value. So the response, Z, multiply the input. All right, see we learning. If this Y do not respond, this Z do not, this 1 is good, or 1 multiply this one, then this one directly feed its bottom-up weight. All right, bottom-up weight is like V1, V2, V3, V4, V5. This 5 neuron feed directly into this. So this is 1. This is why 0. They don't see why this did not link. Why? Because the value is 0. All right, value is 0. Those is not linked, but only this linked. Why? Because 1. All right. So this has a correct linking with this one, and this one neuron did not fire. So it did not really update his weights at all right? This one, the same thing. It's linked with this one, and this is called 0, 0, 0, 0. Right? So all the firing neuron will have this one as the input. If first time it fire, it completely use 1, 0, 0. If the second time to fire, for example, said, suppose this neuron, this neuron second time to fire, the last time it was firing at 0, 1, 0, 0, 0, then this neuron first time has a connection with this one, all right? This weight is 1 because origin firing 1. Next time this is firing at 1, and this weight turns out to be, because divided by the age is half, age is half. First time it was 1, and there's no linking here. Now age is 2, so it becomes divided by age. This is a half. So for this neuron, it memorized this case. This case is that second Y neuron fired. Then the next case, this neuron fired. So this neuron was learning 50% firing for this neuron, 50% neuron from this neuron. All right. Actually, the incremental average was such that it guarantees that for every neuron, the weight is equal to the times the relative frequency for the corresponding neuron fire condition on the post neuron fire, all right? And this one does not change because they're not firing, only firing neuron will change and the following neuron will update weight. So those are the probability. All right, give example, next time, so you give it third time, three times, then this will become 3, 2. This become 1/3. Why? Because you have 3 times. This is 2, this is only 5 twice, this is only 5 1 times. So it turns out that all the bottom-up weight for the Z neuron is the relative frequency. This number is number times this Z neuron fired. This number is the frequency for this neuron fired when it fired, and this is the relative frequency for this neuron fired to this. So you can see that probability computation is automatic. And why probability? In fact, for Turing machine, we don't need to worry about it because a perfect match or a perfect match. But once X is natural, all right? If it's natural, then the match is not perfect. And when we have a real control for Z neurons, not perfect, then we want to find the best match, and this probability will serve as the maximum likelihood estimation, right? Maximum likelihood estimation. And so this is the rough idea without doing too much math. So now you can see that now we have Z neuron, right? And turned out to be, in fact, the Y neuron will estimate the probability for XZ to fall into its von Neumann region. All right, those are the probability, and because you have top 1, then Z neuron, the bottom up weight is relative frequency, and we have already proved that overall network is maximum likelihood estimation if the input is natural. All right, and if it's just learning from a Turing machine, and then learning is if you have enough Y neurons, means that the number of Y neuron is equal to number of transitions of the FA, then the learning is perfect and error-free. That's a very, very intuitive explanation and much easier to understand than the math. All right. Now, why that happened? Because maybe the first page. Because last time, this neuron perfect match input, he claimed that, hey, I'm in this transition table, all right, this transition table, suppose this is the transition table, then these three was presented here, suppose we supervised it, then this particular Y neuron firing will link to all the firing neuron because the weight is perfect, all right, then the fired ideally. So in other words, that this DN1 learns any Turing machine perfect, error-free, and no local minima, because why the number sample is perfect. A number sample is finite, and as long as you have enough Y neuron, all right? And if the input is infinite, then DN1 will compute maximum likelihood estimation, so the transition is based on the finite number of neurons, and in this case, number of neurons is not enough, all right? But it's optimal. So it turns out to be that we solve many problems, and so John probably put me into your thesis, all right? So basically, we solve the curse of dimensionality problem because those features, the more the better, all right? And we overfit it. Some people call it overfitting. But why it's not bad? Because once we have more neurons, and our overfitting with a fixed number of neurons not enough, but we update the weights, and those weights are optimal. All right, so we overfit it, but it's optimal. So there's no local minima to talk about, because it's optimal. Optimal means there's no local minima. Our minima is globally optimal. All right, so we solve a huge problem of the curse of dimensionality. It's highly nonlinear problem, and we do not have a local minima problem. All right, and that's a really big issue here. All right. Another issue is that we learn incrementally. We do not collect all the data, right? X, Y coming in. For example, that we get Z and we X in, and we generate one neuron at a time, and we handle transition to Z prime, and we never had to collect all the X or collect the Z. All right, so this is called incremental. Another thing is that, so just very important, means that if we do not generate that z, we will not get next x. Why? Because this is like moving forward. If you do not know you are moving forward, you do not get the next picture. Or this could be turned left, you do not see the left image there. So this is called align. Right? Align learning means that you need to compute in real time. You generate z, then you get action carried out, you get next x. There is issue of delay. You see that from the we discussed earlier that DN1 have 2 time delays. This one is 1 time delay. The network compute z and x, then this time already pre-action, but pre-action is not there until for top case. Suppose this is a one network update. This is another network update. Z start to compute, all right? But Z cannot wait for Y to finish. Z cannot wait for Y to finish. So network will compute Y and Z in parallel, all right? So actually when T equal to 0, you have X and Z 0. Then T1, you only compute Y. You also compute Z. The Z is for a starting state, actually. When T equal to 2, and the Z computes, Y also computes. Z equal to, T equal to, Z computes, and Y also computes. That Y will be used for Z in T equal to 3. All right, suppose T is like 0, 1, 2, 3, like that. So you can see that Z and Y have 2 parallel computing paths, and they run in parallel. All right. So there's latency. The latency is in this case 2. All right. So the input from X at T0 will appear in Z only at time 2, not Y. Why? We'll only finish Z Y computation. This is called asynchronous. Y and Z are computing parallel. They don't wait for each other. It's called asynchronous, which is very important for real-time computation like GPU. All right, we do not assume that area is waiting for another one. All right, let's move to the next one. Why we discuss that one? Because we want to talk about DN3 now, all right? How much?
We don't have DN3.
So DN3,
DN2.
DN2, I'm sorry. For DN2, we have many neuron fibers now. Right? So Z, we have X. Then you have Y. Originally we talked about even top 1 only for DN1. Now top 2 have DN2, right? So DN2, now this is really exciting. I think this is really exciting. I couldn't even sleep for many days. I'm keeping thinking about what can we do. I'm drawing neurons. There's connections like that. So this type neuron is like DN1, right? DN1, DN1 only connect from Z and X. Then we add Y neurons that can link to each other. So suppose I'm doing this. What does that mean? So Y neuron, Y neuron, Y neuron. And this neuron originally can link to X directly. Now instead it linked from, what's the type? This type is X, Y, Z, 1, 0, 0. Okay. This neuron is 0, 0, 0, 1. So this is the type, only connect to them. And this neuron is 1, 1, 1. 1, 1, because this is connected to the Y neuron. So why do we do this? Very, very important. Extremely important. Let's talk about the first thing. Very important, all right? And that I will. I'm writing something for Fei Li today. I almost finished, and I hope that Fei Li don't get mad. All right? I try to have a academic discussion. Suppose this neuron was supervised by this. All right? to be left hand. All right, this neuron is supervised by this one to be right hand. All right, then suppose this neuron is something that need left hand or right hand. So if linked to this, instead of doing this, I use left. If this one is learning well, it will disconnect it. We will select maintenance gradually because linking has a high variation and this is very stable, and we cut that way. All right. Then this neuron will have something like left hand, right hand, abstract. So suppose this is supervised by this to be, say, hands by a human being, a pair of hands. And this hand has a supervision. If hand is up, and left hand is there, right hand is there, and this one can have many shapes. Suppose left hand has 100 shapes appearance. Right hand has 100 shapes. Then you want a brute force. Suppose this Y handle the entire pattern. If this A requires that, A will require 100 times 100 will be equals to 10,000 templates. But because this is supervised for left, this is only 100, this is 100, and the number of sample you need is only 100. Why? Because this is for left hand. So it's abstract. For A1 and A2, this A1 abstracted. All right, abstract 100. This abstract 100. So this A only need 100 samples. So A originally you need one. Now it goes to 100 samples only. All right. This 100 samples does not have to present all the time. Right? It sometimes is times 3, times 4, doesn't matter because this is abstraction. All right. So this is called a hierarchical abstraction. Then solve the problem that ImageNet has. ImageNet will talk about the global patterns and then how many samples, and there are too many samples for you to memorize anything because do not have network of connected, we call top-down, and supervised by neuron, and the number, this is for a number of pattern you can appear in the human body is astronomical, too many, and this is very manageable. All right, so basically you do abstraction for components, then the object becomes based on the abstracted components, then you can handle scalability. If the entire network is scalable, all right, for very complex network, that's the first thing that we are talking about today, which is it's not a cascade. It's not a cascade like A is a layer and but rather you have a top level down to the low level. See that top directly down there, and the supervised components neurons. Then you can have a abstraction across the internal Y neuron, just like we had before. Now, Or Chen had a paper talk about the group. Say this is object 1, this is object 2, and this becomes group. All right. This is a one concept. This is another concept. Then this is a two combination. Give example. This is object type A, object type B, and this could be relationship. All right. Say object type A play object B. Example. This is a relationship. All right. Not just left hand, right hand, but rather grouping of the relationship according to abstracted components. All right, that's a scalability that I think that's how the brain works. Otherwise, brain cannot function reasonably well in real world. All right.